Hi, my name is Gemma Church, and in this video I will be talking to you about working with graphs and data. Graphs and data and working with measurement are essential tools when working in science, because it is measurement, the way science measures phenomena, that separates it from other disciplines and just simple opinions. With measurable evidence, scientists can make strong scientific claims. The ability for you to work with graphs and data is something that you, as a student of science, will need in both TEP025 Bioscience and in your future studies. In this short presentation, you will find some valuable information that will help you with your upcoming laboratory report. Mainly, we will be looking at collecting data and how to put it into a table. We'll also be looking at how to make sense of this collected data and how you can create a line graph and then understand what it is telling you. Finally, I will walk you through a simple step-by-step guide as to how to create a professional looking graph on Microsoft Excel. This will be important for you when presenting your final laboratory report. On this slide, I have some fictitious data for us to look at. While I'm talking about it, keep in mind how you can apply this information to your own circumstances, namely doing your lab report experiment. In this table, I've recorded the heights of Tommy and Jenny through the ages 10 to 17. So every year on January 1st, I took their height measurements and put them in a table. Creating a table while experimenting is important, as it allows you to concentrate on your experiment while keeping clear recordings. It's no good jotting down some numbers on scrap paper and then later looking back at it and having no idea what you meant. As you can see on this table, it very clearly has column headings with unit measurements in them. As you can see here in the height columns, it states that the numbers in these columns are heights and they are measured in the units of centimetres. If you put the units at the top of the column, you don't have to write centimetres next to every single measurement because it applies to all of them. In this column on the left, it is very clear that it is showing age because it states so at the top of the column, and it also states that the measurement is in years. When I look back at these recordings every year, there can be no confusion as to what I had measured previously. The only thing that I could say is missing from this table is a heading. If there was not this introductory paragraph at the top of the table, people who looked at this might not have any idea what I was talking about. When you do your lab reports, ensure that you have a heading for your table. The heading should go at the top of the table. I'd now like to go into a little more depth about how to create a table. It's important not only for your information, so that you're very clear about what your recordings mean when you look at them later, but also for your reader, because a person coming in who has no idea what your experiment is about will need to have a very clear table with all of the right elements in it to accurately understand what you were talking about. This guide is also useful for you when creating your lab reports, because you will be getting marked on the quality and presentation of your table. I'd like you first to look at the heading. It states Table 1, Tommy and Jenny's change in height during adolescence. As you will notice, it starts off with the words Table 1. If you have more than one table in your document, you should state them as such. Table 1, Table 2, Table 3, and so on. The second thing you will notice is that the title is descriptive. It doesn't just say Table 1, Experiment 1. It describes Tommy and Jenny's change in height during adolescence. This is very important, and you should include this in your lab report. As I already stated in the previous slide, but I'd like you to look at again because it is important, the column headings describe the variable, which is height, and the unit of measurement, which is in centimetres. or the variable, age, and the unit of measurement, years. It's very important that you describe what you're measuring and include the unit of measurement. Also, just to reiterate, because the unit of measurement is at the top of the column, you do not need to write the unit of measurement next to every single number in the preceding rows underneath the columns. Over the next few slides, I want us to start taking a look at line graphs. It can be really difficult to visualise what the data in a table actually means, particularly when there is a lot of it. Most people find it a lot easier to view things when they're on a line graph, so when we can physically see shapes of patterns rather than masses of numbers. You will be required to make a line graph for your bioscience report, and we're going to have a look at one now, so this will give you a nice guide as to how to go about that. If you'll remember from our table, we have two variables here. We have age and we have height. When we create our line graph, we will also be using the age and height. We will just be displaying them along two different things called axes. On the y-axis, which is the vertical axis, we plot the dependent variable. In this case, the dependent variable is height. Now, when we're talking about dependent variables, that means it is the thing that changes because of the other variable, age. So height, the change in height, depends on age. So as the children grow up, as they increase in age, their height changes as a result. It doesn't really work so much the other way. It doesn't make sense to really say height. As height changes, age is influenced, because age is the factor that is influencing the change in height. This can be a little confusing sometimes, so it might be a useful thing to write down and refer to, and as you get more confident, hopefully it will start to make a little more sense. Looking at our graph here, you'll notice that it's got a nice clear heading that says height and includes the units of measurements. Also, our numerical measurements along the side of the axis are graduated evenly. That is to say that they're increasing in this particular circumstance at intervals of 10 centimetres. It's important that they are graduated evenly. Along this axis here, this is our x-axis, the horizontal one, we plot the variable known as the independent variable. This is the thing that we change, the experimenters change, in order to see something happen to the dependent variable. Again, you can see a clear heading. It states that this is age. We have plotted along this x-axis, and it also shows us the unit of measurements again. These are two really important points. Here you'll notice that on neither axis I started at measurement 0. If we were to start at 0, rather than say 120 centimetres and age 10, we would have no data points, because if we go back to our table, you will see that we did not start at age 0 and we did not start at height 0. So because we have no data points for that, it's not really useful for anyone to see a whole massive space on a graph with no data points on it. So here I've simply drawn a little zigzag symbol, and that symbolises that it's a broken axis, and we're starting from 10. The final thing that I'd like you to note is the heading. It's always important to have a heading for both your tables and graphs. With a graph, the heading goes at the bottom rather than the top, and we call it a figure. If we have more than one graph or picture in our document, we label them as such: figure 1, figure 2, figure 3, and so on. Again, you'll notice that it is a descriptive title. It does not simply say experiment 1. So if a stranger was to come and look at this graph, they would know that it was showing the growth of Jenny and Tommy throughout adolescence. Now we're going to look at how to actually plot data on the graph. If you know how to physically plot data on the graph, rather than just letting your computer do it for you, it can aid you in your understanding of what graphs actually mean. Here I've got an excerpt from our table. We're only showing the first row. It should say row, not column. So what we're going to do now is step 1. Find age 10 on the x-axis. So this is our independent variable. So we go to our x-axis and we find age 10. From there, we can draw an imaginary line up like that. Step 2, we find the height on the y-axis. So our height, we'll look at Tommy first, is 132 centimetres. So on our y-axis, we find 132 centimetres and again draw an imaginary line going horizontally. Where those two imaginary lines meet, we draw a simple dot, and that is our first data point. We would continue to plot in this fashion, so if we were to do Jenny as well, it would be wise to use a different colour so that we didn't confuse the data plots of Tommy's with Jenny's. But again, we would go to age 10, draw an imaginary line upwards. We would then find the height on the y-axis, 130 centimetres, and where the two imaginary lines meet, that's where we would draw our data plot. As you can see, this is the completed graph. The part we were just looking at was here. Age 10, Tommy's is the red because it's 132 centimetres at age 10. At age 11, we can see that he's grown taller. At age 12, taller again. At age 13, taller again. This is a much easier format to see the rates of growth of both Jenny and Tommy, as opposed to this style, where we couldn't really see those patterns. Again, you may like to review this chart when creating your graph. It shows all of the important elements that you will need to create a really excellent graph for your lab report. As you can see, there is no unnecessary colour or decoration. You do not need to fill in the background with lots of colours. Here we've made sure that our lines are distinct from one another, and using this key we can see very clearly that the blue line relates to Jenny's growth and the red dotted line relates to Tommy's growth. Again, the x-axis is clearly described and its units of measurements are clear, and the y-axis the same. And again, we have our descriptive title that tells us it is the first figure in the document. This is a good slide. It shows you how not to present your graph. These are some common errors that students make. As you can see here, Experiment 1, that does not give us any description in this title as to what this graph is about. If we didn't already know what this graph was plotting, would you have any idea, any clues as to what it was showing? Not really. Also, the second thing you should notice is that with a graph or a figure, that heading should actually be at the bottom. As you can see here, there is no key or legend, so all we've got is a red and a blue line. We have no idea what these red and blue lines signify, what the difference is. Makes no sense to us. Also, there's excessive use of colour and it makes it really difficult to read. Here, the x-axis is numbered, which is good, but it doesn't tell us any description as to what these numbers mean and what units of measurement they are. On the y-axis, we've been fortunate enough to be told something to do with centimetres, but centimetres doesn't really make any sense just by itself. We need some numbers, and we also need to be told what it is we're measuring in centimetres. We're measuring height. What I'm going to show you now is how to make a really professional looking graph, line graph, using Microsoft Excel. You should follow this guide when producing your lab report. What I've done is I've inserted the heights of Tommy and Jenny into this Microsoft Excel spreadsheet. What I'll next do is highlight that data, click Insert, select a line graph, select this simple line graph, and there, it's inputted it for me. However, if you're paying attention when we were discussing the important elements of a line graph, you'll notice that there are some very important things missing. The first thing that I don't like about this graph is that it starts from 0. We don't need all of this information because our smallest height is 130 centimetres. Select that y-axis, format the axis, and here we go. We can select our minimum value, and I think 120 centimetres is suitable. I'm also not happy with the x-axis. As you can see, it just numbers year 1, year 2, year 3, and so on. I want this to say age 10, age 11, age 12. What you can do is select that, go to Design, select Data, and you can edit the horizontal axis. What you need to do is put in a bracket and list the numbers as such that you wish it to display. Make sure you use commas and brackets. And here I will display them. And now we've got the axis that we like. The next thing that we're missing are our axis headings. You can cheat. Instead of having to manually input them all, you can find a graph that might have them. But again, there's parts of this that I do and don't like. You don't need these. Delete those. Make that a bit bigger for you to see. Axis title. This is our age, and our unit of measurement is in years. Beautiful. Close. Here, this is our height, and that is in the units of centimetres. This chart title, it's good, but it's in the wrong place. Let's drag that down below. It's the first figure in our document, so we'll call it Figure 1. Growth of Tommy and Jenny during adolescence. I'm not sure if I spelled adolescence right. Give that a bit more space. This is excellent. This is a key. Again, we've gone to select data, edit, series name. The blue line was Tommy. Okay. Select data, series 2, edit, Jenny. Okay. Now this graph has just about everything that it needs to be a good graph. You can even copy that straight from Excel and put that into a Word document. So if you're processing your lab report in a Word document, it transfers easily over. The final thing that we're going to look at is making sense of our graph. You'll need to write a short paragraph underneath each of your graphs describing what is in it. This information should only pertain to information that is exactly in the graph. You shouldn't make any reference to your opinions or to work in literature. It should just be purely describing the information displayed on the graph. Let's analyse this one together so that you can get an understanding of what you need to do in your lab report. Let's analyse the blue line. This is Jenny. This steep slope between ages 10 to 12 indicates that she increased in height quickly between ages 10 to 12. It's a steep slope. As you can see here, after age 12, she still increased in height between ages 12 to 13, but at not quite as steep a slope. This is to say that she did grow in height, but at a slower rate. Finally, between ages 14 to 17, we have this straight line. This straight line indicates that she did not grow at all. Now, what do you think the steep red line between ages 13 to 16 indicates happened to Tommy? How can you compare Tommy and Jenny during this same time period? So now we're looking at Jenny between ages 13 to 16, based purely on this data. Have a think about that. I've got an example of a good answer and a poor answer, hopefully to give you an indication of the sort of thing you should write about in your lab report. A good answer only includes facts from the graph. And this one states, Tommy's height increased at a greater rate between ages 13 to 16 than he did between ages 10 to 13. Let's just have a look at that. Indeed, Tommy did increase in height at a much greater rate between ages 13 to 16, as we can see by this steeper slope, than he did between ages 10 to 13. Back to our answer. Tommy grew at a greater rate between ages 13 to 16 than Jenny did. He increased height by 29 centimetres over the 3 years, whereas Jenny only increased in height by 2 centimetres. Again, age 13, whilst he is shorter at age 13 than Jenny is, this steep line indicates that he increased by 29 centimetres between age 13 and 17 or 16, was it? Whereas Jenny, between ages 13 and 16, only increased by 2 centimetres. So yes, that would be a good answer. A poor answer, it includes some information that is found in the graph and also some that is not found in the graph. So Tommy's height increased at a greater rate between ages 13 to 16 than he did between ages 10 to 13. Well yes, that's fair, that's valid. Tommy grew at a greater rate between ages 13 to 16 than Jenny did. Yes, again that's valid. But this next bit, this isn't. These results are not surprising, as on average girls undergo a large growth spurt a few years before boys do, coinciding with the onset of puberty. And it's got a reference there. That might be valid in your discussion, but when in your results section you're writing about what's in your graphs and tables, you should not include any information that is not included in your graph. I hope this information helps, and if you have any more questions, please don't hesitate to use the discussion board or send an email to one of your lecturers in the bioscience team. Thank you.